Okay, we'll go ahead and get started for real, whatever time it is. Yay, so anyway, we want to follow up on the sequence of the workshops here. We've been dealing with this, we should be to session 6 now, looking at specifically convective mode. And what I'd like to do is again, like we've been going on the last couple, a little bit of conceptual model development, but mostly some practical applications of these concepts. So we'll go ahead and get started here. Just to remind everyone, we're in session 6, which is, we've got 3 more after this one. There'll be a break next week, and then the last 3 will be sequentially April 7th through the 21st. All right, here's an example, some storms. This is a late summer case, and what I want to do is we're going to kind of step through why the convective mode matters and why it's not necessarily a simple thing to figure out in every particular case. So we start off with a scenario where we've got clusters of storms in northeast Nebraska. I'll show you some more data in a minute. This is essentially on the surface cold front, and there's another little broken band of storms on the Kansas-Nebraska border that looks a little more cellular, and that's on a surface lee trough remnant dryline feature. Moderately interesting environment downstream over the Missouri Valley with SIGTOR values in the 3 to 4 range, which gives you at least some potential for significant tornado development, assuming you get the right mode of storms moving into that environment. All right, 1 hour later, storms have continued to grow, upscale a little bit. We've got more of a line segment in northeast Nebraska. Again, somewhat of a broken line segment down on the Kansas-Nebraska border. The environment looks a little even more interesting downstream. The combination of buoyancy and low-level shear continue to increase. So at this point, if you get discrete storms moving into that environment, you might be concerned about tornado potential. 23Z. Okay, now I've highlighted 2 storms that we look at. Not too much detail in terms of radar, but just to highlight how the environment behaves and how these 2 storms behave. We've got one storm that did have a mid-level mesocyclone that's northeast of Omaha, the northern storm of the 2 highlighted, and then there's another storm in southeast Nebraska that's somewhat discrete. So if you just take a snapshot of this environment, you see SIGTOR values on the order of 9, which is probably 95th percentile for that parameter, 4 significant tornadoes, so that's way up in the distribution. Large low-level shear, strong deep layer shear, large buoyancy, low LCL height. So this is a favorable environment as we understand it, and we've got what looks like a semi-discrete storm moving into it. So you would think, based on the snapshot, gee, we might have a tornado problem. Now this is where convective mode and storm interactions come in. We have to look at, first, what happens over the next hour. The storm doesn't stay discrete because of the mode of the convection to the west overtakes it. So in this case, before we ever get a tornado and the supercell process is firmly established, we actually change the mode of the convection. So it becomes absorbed into the line. And also notice what's going on in southeast Nebraska with the other storm. It's staying somewhat discrete, but what's occurring with the environment? Is it changing with time ahead of the storm? So you have to consider how the environment's evolving, and these snapshots aren't going to give you a whole lot of help if you apply them in isolation. So here's a case where we go back. Again, just go to this point. Looks like a pretty dangerous environment. We've got sort of discrete storms, and you would think surely there'll be some tornadoes. Turns out there were no tornadoes. We had several storm mergers. The environment weakens with time, and we get no tornadoes. So it's something that you actually have to consider having an expectation for a scenario like this. All right, so again, just to summarize what was going on in this case, we had the lead supercell in Iowa overtaken by a line segment coming out of Nebraska. And we'll go over the conceptual model stuff. The shear vector orientations up north favored more of a linear mode, and what looked like a good environment to the south and east of the storms actually changed for the worse over time. So the time trends were not favorable for tornado formation, and the changes in mode with time were not favorable. So again, it's not as simple as saying, ooh, I've got this bullseye of STP and storms, therefore I will get tornadoes. Okay, so let's talk about a conceptual model for forecasting convective mode. We're going to discuss deep layer shear vectors and the deep layer mean wind. I don't really show those plots here, but we'll deal with some of it. And the question here is, how much do the storms interact? When they're forming, how close together are they? How much do they interact in terms of outflow and rainfall production? How many storms form? That's a big question in the first place, is if you have more storms, there's more possibilities for interaction. And then can the storms move away from the zone of initiation? So you can almost tell from this recipe that I've built that storms forming in the open warm sector, again, you're missing the ingredient 2 here, where there's not strong forcing for ascent. Chances are storms are almost always going to be discrete. So we're going to focus on boundaries where we have more identifiable zones of ascent, not something super subtle, which almost always initiates discrete storms. All right. Here's a pretty typical illustration of a linear convective mode setup. This is a case where I've drawn in a cold front, and I'm not picking on Illinois or if someone's offended. It's just, I had a dry line over here, but it was pointed out to me that dry lines never get that far east, so I acquiesced, and I put the dry line back in Kansas and Oklahoma where it belongs, but you'll see that in the next example. This one, we've got a cold front, oriented mostly east, northeast, west, southwest. In this case, I've drawn in the shear vectors. The key here is note the color coding. This is going to be the same throughout the presentation. The purple arrows represent the 9 to 11 storm relative winds. So this is up near anvil level for a typical storm. The 0 to 6 is the light blue shear vector, the storm motion in yellow, and then we put the boundary motion as the thick blue line. So what we're doing is we'll show the same sort of stuff when I look at some photographs in specific cases. But here we have a cold front. We have a nice focus for ascent in a band in the low levels, tend to initiate a lot of storms. It's not too surprising that the shear vectors and storm relative winds would be somewhat parallel to the boundary, because if we think all the way back to session 1, you think about the relationship between the deep thermal gradients and the jet structure and everything else. The jet's going to be aligned along the thermal gradient. If you have a front that's reflective of what's going on in the deeper troposphere, the flow should largely parallel it. So in this case, it's not surprising that the shear vectors and the deep layer mean winds are aligned along the boundary. So this is a pretty typical setup for linear convection. So again, just to summarize this, you want either deep layer flow, the shear vectors parallel to the initiating boundary, which suggests that storms will interact and overlap rather easily. If you have strong convergence along the band, then you might initiate a lot of storms. And then just as important, if the storms stay in the zone of ascent, you tend to accumulate convection over time. So instead of storms moving away, you just keep forming more and more storms over time. Here's so this dry line was sitting in the exact same anchor point in Illinois, but we bring it out here, so we'll show our planes biased, at least briefly. These are essentially the same shear vectors in terms of magnitude and the changes with height, or with those. However, the only thing that's different is the orientation of the initiating boundary and the motion of the boundary with respect to storm motion and the shear vectors themselves. In this case, we have a lot more cross-boundary flow. Anvils of the storms tend to go off perpendicular to the zone of initiation, so there's less chance they're going to interfere with each other. We've got storm motion that's faster than the boundary motion, so storms tend to move out of the zone of ascent. You don't tend to accumulate a lot of storms. And we're assuming in this case that we're talking about supercell wind profiles to begin with. So if you piece this all together, this is a case where you would tend to initiate more discrete, widely spaced storms that have less interaction between one another, and then they tend to stay discrete. All right, so just summarizing that stuff. Again, it's just sort of taking everything we had with the cold front linear case and turning it about 45 to 60 degrees, and then providing a weaker source for initiation to get fewer storms, and a boundary that moves slower so that storms can move out of the zone of ascent. So hopefully that makes sense, because what we're going to do now is we're going to look back at that first case, some of the details, and then I'll show you several other more prominent cases of convective mode and how it was impacted by applying this conceptual model. Okay, so this is the previous case. We jump back to, this is late August of this past year there in Nebraska, Kansas. So I've sketched in the surface boundary. So you see the cold front and the remnant lee trough. And over time, we see convection developing, spreading eastward. Now you notice in this case that storms form on the two boundaries, but you can say a lot from looking at the satellite image. How did the anvils respond with respect to the boundary orientation? Are they streaming away from the boundary? Are they staying along the boundary orientation? That sort of thing. How much do the storms overlap? And in this case, you notice up north, the storm relative winds, it suggests they're weak because the anvils are kind of spreading somewhat equally in all directions and they tend to overlap. Down south, a little bit more cross-boundary flow, but it's still not strong. Storms initiated very close together. Okay, so we'll put in some of the mesoanalysis stuff from SPC. This is the surface convergence. We've shown this many times before, and I sketched the boundaries there, the cold front in blue and the prefrontal trough in brown. Convergence marks both axes, so we have a consistent zone of inferred low-level ascent based on the low-level convergence, at least through some depth, based on mass continuity. So we have a reason to get storm initiation given other favorable thermodynamic characteristics. Now, looking at some of the shear vectors, in this one I'm not showing the 0 to 6 shear, but we'll use the effective bulk wind difference, that actual effective shear vector. I've sketched in, I know the little wind barbs are a little hard to see, but I've put in some arrows that sort of summarize what they look like with respect to the boundary. Up north, they're largely parallel, so this would suggest, again, precipitation that's forming is going to be going downwind and generally in the direction of new cells as they develop, and a little bit more cross-boundary flow to the south, but the shear gets weaker as you go southeastward. Storm relative winds up high, same sort of case. In this case, it's actually an antifrontal type flow regime up north where the storm relative winds are actually back to the left over the cool air. And down south, they're a cross-boundary, but again, it's sort of in the noise level. We're getting kind of in that transition zone between a clearly linear or clearly discrete favoring environment. So again, that brings us to the point that there are no unfailing threshold values. You can apply this stuff, and in most cases, you're going to get mixed signals. And I actually grabbed some graphics for this evening, this afternoon. I threw them in so we can look at the Missouri convection from earlier this afternoon when it formed and compare that to the conceptual model. But the idea is look for the most obvious discrete or linear cases where the shear vector and flow orientations are much less than 45 degrees, much more parallel, or much more clearly across the boundary. Again, cases where there's well-defined, strong, low-level forcing for ascent, and the thermodynamic environment makes it easy for storms to generate. So the idea when you're looking for linear convection, the most easy to forecast cases are going to be the most obvious ones. I know that may sound kind of trite, but it's the truth, and you have to keep that in mind when you do the forecasting because a lot of times you get mixed signals. And you end up with mixed modes, somewhat like what you saw happening there on the Kansas-Nebraska border, where it's not clearly discrete, it's not clearly linear. Okay, so we'll go through a handful of severe weather events and look at how this stuff all lines up and how you could use it. And again, I'm focusing on observed data. We're not looking at the numerical model stuff yet. We're going to save all that for later. Big tornado outbreak, we've shown this several times in several different ways in the other presentations. We'll continue with it this evening. Again, you can almost track out multiple long supercell paths with the tornadoes. So this is a case where clearly we had a lot of discrete storms. So you would suspect that it looked rather classic, and indeed it does. So here's just a reminder, 12Z that morning, strong shortwave trough over the Red River Valley, Texas, Oklahoma, moving eastward. Flow largely out of the west or west-southwest through the mid-troposphere. And again, it was this wave over the Red River Valley that progressed eastward to the Mississippi Valley during the afternoon and evening. Okay, we'll jump ahead to roughly the beginning of the tornado outbreak. This is 19Z. I've sketched in the initiating boundary. In this case, it's a prefrontal trough. The cold front would be a little bit to the west of my purple line there, which is kind of my neutral color, not trying to note anything particular as far as the structure of the boundary, but in this case it really was a sort of a remnant dry line-like features, and at least statistically that tends to favor more discrete modes right off the bat. So we look at the orientation, it's more of a north-northeast, south-southwest orientation, western Mississippi, almost north-south as you get into northwest Mississippi, very moist warm sector to the east of the boundary, and I didn't sketch in the remnant outflow warm front across northern Mississippi and northern Alabama. Because again, we're talking about where the storms were initiating to the west. Convergence field is rather modest. This isn't what we call a strong convergence case in the low levels. So this, again, sort of fits the mold of an old dry line where we have modest low-level forcing for ascent. You wouldn't expect storms to erupt everywhere instantaneously. It is uncapped, large cape, big area. This is the kind of scenario where you'd also want to be careful looking ahead of the boundary out in the open warm sector, and indeed storms did form. Again, they're almost guaranteed to be discrete in that sort of scenario, and that occurred on this day. Now looking at the shear vector orientations, big angle, at least 60 degrees, maybe 75 degrees across the boundary, way into the supercell parameter space, no question about that this is a highly favorable supercell type environment. We continue up. We'll look at 0 to 8. Again, there's no magic layer that you have to look at. This is based on the work of Dial and Racy from SPC. They looked at some little bit different, more non-standard layers, but the same thing's reflected in these things that you can pluck off the SPC mesoanalysis. The point here is that the deep layer shear vectors are largely across the boundary. So this would suggest not as much competition or interaction between the anvils and any sort of influence on adjacent storms. The storm relative winds, again, almost directly across the boundary. So all of the shear wind orientations would suggest discrete. We have strong, large cape and relatively weak low-level forcing for ascent. So everything's lining up with a discrete mode in this case. And we had a sounding, because it's a high-risk day, so we have Jackson. And what I want to do is show how we can apply this stuff to the hodograph. And you can look at it in a specific case. So Jackson is kind of on the south end of the initiation zone for this one. Okay, so we're zooming in on the hodograph, and you can, if you see it it's kind of subtle there in the background. We've got the same wind profile, and what we've done is I've put in the orientation of the dry line to the north of Jackson with the speed of the motion of the boundary measured from observation. So an estimate that's moving east, it's a north-south boundary moving east at about 20 knots. So what we've done here is we transpose the shear vectors and the storm motion relative to that boundary motion. So the idea here is how does everything line up relative to the boundary? This is the 0 to 6 shear vector. So again, it's the same thing that you would see. We've just moved it from the origin out to where the storm motion is. So it's just a vector subtraction here. In this case, large angle relative to the orientation of the boundary. And it's well into the supercell range if you can just eyeball that, and that's 50, 60 knot, 0 to 6 shear. The storm relative wind, same sort of orientation, not quite perpendicular to the boundary, but pretty close. Storm motion, again, transposed relative to the motion of the boundary. The supercells are actually outrunning the surface boundary where storms are initiating. So we're just using the assumed bunkers right supercell motion as a first guess. So this case, everything would say a few storms form, anvils and precip areas don't overlap and interact much, storms move out of the zone of ascent, they should stay fairly discrete. Okay, and then satellite, we'll have to focus down on the lower left here. It's in Mississippi. If you just look at the orientation of the anvils compared to that first case we showed, notice that this one, they're stringing off parallel to each other, but not overlapping so much. And you see the storms initiating in several little streamers moving in. This is pretty typical of the moist storm sector down there. Again, you don't see one real solid band that everything's initiating on. So it's a pretty typical case of what it would look like. And in the plains, if you just add a little bit more convective inhibition, a little bit more cape, storms would probably be a little larger and a little more widely spaced. That'd be the only difference. All right, so again, just a summary of the case, large cross-boundary flow and shear vectors, weak cap, but also weak low-level ascent. So we don't initiate too many storms. The ones that do initiate move away from the boundary. And all of this adds up to a dangerous tornado outbreak when you consider the downstream environment. And again, we initiated a whole bunch of storms like this on this day, and that's why it turned out to be such a damaging event. Okay, May 10th, we'll jump out here to one with a little more local flavor. Certainly if you live in East Norman, this had local flavor, or more if you had to replace your roof. This one, again, you see strings of tornado reports that identify individual supercell paths, so you can infer from the reports themselves that these were discrete storms. And let's look at how the environment lines up with that. Again, same sort of thing near the Four Corners, shortwave trough moving, will be translating eastward. You could just infer from the orientation of the flow, and indeed it made it to Oklahoma during the afternoon. Again, we jump to roughly initiation time. I've sketched in the primary initiating boundary. In this case, it was more of a dry line. And mostly, there's a little curvature in the float, but it's actually more of a north-south boundary. Moist sector is not quite as broad as the previous case, and we'll look at the buoyancy as well. But the idea is we have a favorable downstream environment. For storms, stronger convergence in this case, the vorticity is the one that stands out, but the low-level convergence in the red contour suggests it's a little bit more convergence than the previous boundary, but still the orientation is one of the things that we need to keep in mind here. Now notice here we don't have as big as an uncapped warm sector. It's mainly just the area a few counties east of the dry line, and not a huge area north-south, but very large buoyancy over 4,000 Cape, and clearly a supercell type environment when we look at the shear vectors. Now in this case, the shear vectors are almost perpendicular to a lot of the boundary except down south. So again, this first guess, you would think these storms would try to stay somewhat discrete based on this. And again, these shear magnitudes are about the same as the April 27th case. 0 to 8, same kind of thing, so no real big change in the shear vector magnitude or orientation, just a little stronger as we look through deeper layer. Storm relative winds, modest, but again, oriented across the boundary. So far, we've built up primarily a discrete mode argument, even though the convergence might be a little on the strong side on the boundary. Again, the beauty of these big days, we get special soundings and nice locations. So we have a 20Z Norman sounding. We'll look at that one and see how it compares to the previous case in terms of the expected convective mode. Okay, remember, same conventions, and we're going to use this throughout the presentation. 0 to 6 shear vector. Again, largely perpendicular to the boundary, maybe slight, not quite that, but something on the order of 75, 80 degrees. Plenty of deep layer shear vector magnitude. Storm relative winds oriented almost parallel. This is, again, pretty similar to the previous case. And again, the storm motion. Even though the boundary in this case is moving east at 25, it's a little bit faster, but the supercell motion is still faster than the motion of the boundary. So storms may have a chance to actually outrun this, and some of it may depend on how many storms form initially. Okay, so we look at the visible image. So we'll start around 2015. This is when the first storms are going up, and you notice that we tend to initiate in several little points. This is clearly reflective of mesoscale ascent. This is not reflective of strong deep layer forcing for ascent. And just to remind everyone, going back to the sounding, this sounding does not look like one that has had deep ascent acting on it for very long. There's a very moist boundary layer, but then just the elevated mix layer, we don't see the characteristic deep moistening with time from below. So everything even though this is a little east of the dry line, this just suggests, in this case, it's the dry line circulation itself is what's initiating the storms. It's not the synoptic wave per se. But you notice the anvils, they stream off generally to the east or slightly to the east-northeast. The storms they're separated wide enough spacing that they don't really interact. And eventually the thin anvils overlap one another, but not the precipitation areas. So again, it's very similar to the April 27th case, except the low-level convergence is a little stronger, but we didn't have quite an easy an environment to initiate storms because it's not quite as moist and there's a little bit more convective inhibition. So those two factors maybe cancel each other, and we end up with roughly the same type outcome. All right. You knew I had to change gears sometime in here. We'll get away from the discrete ones, which are too easy, and let's get to some messy stuff. Go back to the fall of 2010 in the Ohio Valley. A lot of wind damage reports. There's several short-track tornadoes, but we'll take a closer look at this case and see how this one played out, if you don't remember it. Very strong shortwave trough, speed max coming out of, flow is well in excess of 100 knots at Springfield that morning at 500 millibars. Very strong flow and gradients. This is an intense synoptic wave. I believe this one had a very deep cyclone with it. I think we showed this one for cyclogenesis as one of the examples of a classic evolving mid-latitude cyclone. So this shortwave speed max is going to move out in the Ohio Valley during the afternoon.
Is this the one that broke the pressure record?
It was close. It may have been up north. It was a very deep low. I thought it was on the order of 965 to 970, so it was pushing it. It might have actually been this case. Yeah, I think this case may have been that pressure record. I'd have to go back and look at the details, but this is the same case that I showed several sessions back. Okay, so we sketch in the frontal boundary here. It's a weak cold front. This isn't particularly strong frontal zone. I mean, the temperatures don't drop dramatically, but there is a temperature drop with the moisture drop in the wind shift, and it's oriented mostly north, northeast, south, southwest. Difference between this and the other cases is while we have 60 dew points in the dark green, the dew points really are just barely low 60s, no more of this 68 to 70 stuff, and we don't have the lapse rate profile either. Convergence is modest. It's actually weaker than the Oklahoma case I just showed and sort of in between the two previous examples. So initially, you don't have enough information to say whether this should be linear or discrete convection based on what we've looked at so far. Now, this is a big difference compared to the previous cases. Meager buoyancy, 250 ml cape, that's to 500 maybe. Again, the lapse rates weren't particularly steep. There's convective inhibition everywhere east of the boundary, so it's hard to initiate storms anywhere other than on the wind shift itself. So that's one of the factors that probably plays more into a pushing things toward a linear mode because we can't get storms anywhere but along the boundary. Now when we start looking at the shear vector orientations, it's actually a supercell wind profile. If you look at the magnitudes, that's 40 to 50 knot 0 to 6 shear that extends out over the worm sector. However, look at the orientation of the vectors. The wind barbs are largely out of the south-southwest along the length of the boundary, so the cross-boundary flow or shear vector orientation is very small. Same sort of thing at 0 to 8 kilometers. It's, again, much more boundary parallel type orientation, and the primary speed max is clearly back to the west of the front itself. And the storm relative wind. So we've got everything kind of lines up where it's sort of boundary parallel, the strongest flows back to the west, and we're only going to be able to initiate storms in the zone of ascent right on the boundary. Well, some of that you can see from the sounding from Wilmington that was launched mid-morning. Again, strong vertical shear, but buoyancy is rather weak. And again, this is a case where you might have trouble sustaining supercell structures just based on the thermodynamic environment. So that might be a hint right there that a linear mode is more the preferred outcome, even without considering too many other factors. Okay, we go about the photograph. This one looks a lot different than the previous one. 0 to 6 shear, maybe 20 degrees offset between the boundary orientation. In this case, it's moving east-southeast or southeast at 25 to 30 knots. So the storms the anvils of the convection would tend to overlap. The storm relative winds are on the weak side, and even if you did have a supercell, which may not even be relevant in this case, the storm motion actually lags behind the boundary. So this is a case where a right-moving supercell based on the bunker's motion would be undercut by the front. So that's not a clean scenario to maintain discrete convection. And if we look at this, we see really the anvils are not particularly evident because the convection is relatively shallow. And when we go to the radar, this is another thing that plays a big role in convective mode. How did the storm start? Well, this is going back 12 to 18 hours earlier. The initial storms initiated as a convective line back in Missouri and Arkansas. That structure was maintained throughout the entire event, and we were just unable to initiate storms ahead of it except down south where the wind profile wasn't as favorable anyway. So again, just go through. So this is one where it does pay to pay attention to what's going on even the previous evening. I know I've harped on source regions and all that. Look at the full evolution of the convection. So any piece of information the atmosphere provides for you, take it into account because it could be important. All right, so this one, a little different recipe. It's a squall line the whole time. There's much more boundary parallel shear vectors and flow. It's a weak cap, but there's only weak buoyancy, kind of competing factors. Low-level convergence is modest, but again, combined with everything else, the only place we can get storms is on the wind shift. And given the fact that we had a well-established cold pool with the squall line to begin with, it's going to be really hard to undo that in this kind of profile. All right, another one down south, messy one. I think this might be the record severe report day. It was 1,200 and something individual reports, mostly wind damage, a few tornadoes in there, but not the big swaths of tornadoes that you've seen in the big outbreaks. Shortwave trough, a little bit more positive tilt type wave across the plains. That's moving toward the Mississippi Valley during the day. We jump ahead to 18Z, close to the time. Storms are already going at this point, but this is relatively early in the event. Notice the orientation. It's much more southwest-northeast. That looks a lot like the orientation of the 500 flow. So if we just step back real quick, you can already tell that the flow in the mid-troposphere is largely parallel to the boundary. Again, this is a cold front case. Modestly moist warm sector to the southeast of the boundary, but we'll take a look at what a sounding showed there. Convergence a little stronger northwest Mississippi. It's not outrageous, but we do have some focused descent implied along that, or inferred in the boundary there. Now, we do have buoyancy, Mississippi into Louisiana, moderate Cape at 1,500 to 2,000, according to the SBC mesoanalysis. And it also shows that it's relatively uncapped. Now, remember, when you have observations, be careful to cross-reference these profiles with what observations you have, if possible. 0 to 6 shear. Now, this looks a lot like the Ohio Valley case, except in this case, the shear vectors favoring supercells don't even extend very far in the warm sector. They're almost identical or parallel to the boundary, so the orientation is almost the same. 0 to 8 kilometers, same sort of thing, and the storm relative winds are anemic out in the warm sector. So you would think in this case, storms are going to form, precipitation is not going to be lofted very far away, tend to rain out close to the updrafts, and what the movement there is stringing out along the front. And here's the sounding from Jackson. Now you notice that the mesoanalysis showed 1,500 to 2,000 ml Cape, and it was uncapped. This is using the most unstable parcel. So if you look at this, there actually is inhibition, and the level of free convection is very high in this sounding. So that would tell you that it's probably going to be hard to initiate pre-frontal storms in the warm sector, because how are you going to get a parcel to the LFC in that kind of profile, if this is indeed representative, and I think it was. So we don't have large Cape. The shear vector orientation suggests a line, and that looks like the only place that we can initiate storms consistently is on the wind shift. So we'll take a look at how that turns out. In this case, the shear vector orientation is a little, not quite as hostile based on specifically the Jackson hodograph, but the storm relative winds are still on the weak side. The preferred estimate of supercell motion does not get out of the zone of ascent. So this is one with some slight mixed signals, but overall, everything would lean toward a linear convective mode. And sure enough, we had an extensive squall line. There were some semi-discrete elements back in Louisiana, but they didn't stay that way for very long. And that's where the more significant tornadoes were. So again, storms just kept forming to the southwest, moving northeast along the line, interacting with each other and reinforcing the cold pool and keeping the whole structure going. And then just again, another summary, as I've done with the other cases. Just, you can see there that again, it's primarily a recipe favoring more linear convection. And again, it's because storms accumulate along the front, and this isn't really a favorable profile for warm sector supercells. All right, May 23rd of 2008, we'll look at one that actually displayed two different cases for mode evolution within the same event. You see what looked like several supercell tracks. This one had a whole series of tornadoes. I think this is Kansas's biggest tornado day on record in terms of numbers. And we'll look at the two episodes that occurred with this one. A little bit different flow regime than the previous ones. Big low over the Intermountain West, Great Basin. Some people might complain that the flow is too meridional over the high plains, that sort of thing. Well, of course, keep in mind with that sort of flow regime, that's one way you get the moisture further west onto the high plains. You don't end up with a lee trough sitting out at I-35. It's kind of hard to be moist if the lee, and western Kansas, if the lee trough is out in the I-135 corridor. So just keep in mind, you don't immediately shut down a pattern just because of the orientation of the 500 flow. And just because it's meridional does not necessarily mean it's going to be linear convection, as we'll see. Okay, we go to mid-afternoon, surface dry line. In this case, it's a somewhat ill-defined dry line. The trough is relatively weak. The winds you can see from the wind barbs, if you pick those out, they're largely out of the south on both sides of the boundary. You would suspect that the convergence would be weak. And indeed it is. We see the vorticity field, but the convergence is, other than the boundary intersection up toward I-70, it's relatively diffuse dry line. Moderately to strongly unstable, relatively uncapped over most of Kansas, so it shouldn't be too hard to initiate storms. Shear vector orientation well into the supercell range, oriented largely across the boundary. Even though the 500 flow was out of the south-southwest, the shear vectors are more southwest-northeast. So there's a pretty large component across the boundary in this case. Same sort of thing with 0 to 8. It's 45 to 60 degrees across the boundary. And again, especially up into Kansas, you're well into the supercell range. Storm relative winds, same thing. So they're all kind of aligned in this case. All right, we had a sounding from Dodge City, again, a bigger day, so we get special soundings, and this will help us look at the environment. You can see large buoyancy. Hodograph is not particularly large, but the deep layer shear is in the supercell range. If you just take the green and the red segments, that's at least 40 to 50 knots in length if you just did a little quick eyeball shear vector calculation. Okay, so what does it look like? This case, the dry line actually arcs back north-northwest, south-southeast. So we've turned everything on its side slightly. Shear vectors, large angle across. Storm relative winds, not particularly impressive based on this sounding, but more importantly, storm motion keeps storms off the boundary because this boundary is barely moving. It's just sitting there. So the storms are just forming and moving out of the dry line zone. So we've got weak ascent and storms forming in the same place, so you would suspect it would just launch multiple discrete supercells out of that profile. And indeed, looking at visible, that's what happened. You can sort of see down there, and even in the northeast panhandle, southwest Kansas, it just doesn't go anywhere. So you get big supercell forms and moves off, and then occasionally new storms form in the same zone. So again, this is a pretty typical recipe out closer to the high plains for discrete convection. And again, just to summarize that, again, slow-moving boundaries are more favorable, obviously, and it's easy for storms to move away from the boundary, and in this case, most elements were fairly solidly in the camp of discrete convection being maintained. Now the question is, did it look like that the entire time? So we've got this one went on long enough to where the 0Z obs are relevant. So we can see that there had been a speed max back toward Arizona. That's now made it out into the Texas Panhandle. There have been some height falls. So we've had some large-scale influence. Flows a little bit more southwest than it was in the morning out in the Panhandle, but it's more southerly up toward Nebraska. So there's a shortwave trough axis you can infer across western Kansas. Now we've got two boundaries. I've sketched in what we see as of the late evening. The surface cold front becomes involved in this. And that's the western of the two boundaries, and there's actually a boundary merger. So the cold front overtakes the quasi-stationary dry line. Still have the same type warm sector, dew points mid to upper 60s, even some low 70s down in Oklahoma, east of the boundary, and it's still somewhat unstable. Now you see in this case, don't get fooled by the vorticities, the color fill, remember, but the contours, convergence is much stronger than it was earlier, and that's on the cold front, and that's as it overtakes the boundary. So now we've got a lot more focused forcing for ascent in this band as the cold front arrives. Convective inhibition has come up because we're getting later into the evening. Still strongly unstable to the east, but okay, so now it's going to be harder to initiate storms east of the dry line or anywhere else. So we're probably stuck with just the existing storms. Whatever was going by this time may hang around a little while. Again, think back to session 4, the pressure perturbation, the storm's drawing air in and up to its own LFC and keeping itself going. And as long as the inhibition is not too large and the LFC is not too high, or the vertical shear doesn't weaken too much, this process can kind of keep itself going in what looks like a somewhat capped environment. Shear vectors, they actually look more favorable for discrete at this point because it's much more cross-boundary. This is looking at 0 to 6. Again, the angle's probably 75 degrees across the boundary. Now, not so much on the cold front, but even where the cold front's catching up to the dry line. 0 to 8, same kind of thing. And the storm relative winds, again, mostly out of the west-southwest. So the shear vectors might say discrete, but we've got much stronger low-level forcing for ascent imposing its will on this situation. And here's the Dodge City sounding. Much bigger hodograph than we had earlier, still large buoyancy, but let's look at how everything lines up here. Again, like I said, this looks even more favorable for discrete storms than the earlier example, aside from this one difference. That's the bunker supercell motion for the same wind profile is now lagging behind the boundary. So the cold front's moving east faster than the storms are. The storms are moving much more to the north than the east. So if we start initiating storms on the cold front, and it continues that eastward motion, it's going to essentially undercut all the convection. And sure enough, we look at the satellite image, and you can see right in there that solid band of new updrafts. That's essentially the reflection of the front. So you see the big supercells that came up diurnally on the old dry line. We quit initiating new ones, but now it's that solid north, northeast, west, south, southeast band, which represents the strong forcing for ascent with the cold front. And like I mentioned in the case for the Ohio Valley, it's some of the impacts of these changes in convective mode have a big influence beyond just the day you're looking at. So we see the supercells relatively quickly. In 30 minutes, the squall line pops up on the front. And again, there's no way for storms to move off the boundary. It's hard to establish the supercell process. So it sort of changes the mode, and then the tornado outbreak goes until the pre-boundary storms weaken, which was kind of late evening. Interestingly about this case is you see the line of storms going in Oklahoma. This is what produced the outflow that left the outflow boundary for one of the boundary tornado cases that we looked at in the synoptic session. So the change in mode from 12 to 24 hours prior to that in western Kansas is what got everything rolling for an outflow boundary focused tornado event in Oklahoma the following day. Again, if you're not looking at this stuff and anticipating it, it's very easy to lose this stuff, the details. You focus too much on the discrete storms, you lose track of how this might play out and whether you would expect this convection to remain linear. Look at the orientation of it by this point. If you recall all the shear vectors, everything else, you would suspect that a linear mode would be maintained from here forward, and indeed it was. Okay, so again, just the final summary of this case. We've got, some mixed signals, but most importantly, stronger low forcing for ascent and faster movement of the boundary were probably the two key elements in forcing this over to a more linear mode with time. But again, the wind profile looked like supercell. Now we'll look at today. I had some time to grab this one. We'll just throw it in here since I know some of you are probably sitting there staring at it on your phone. Hopefully that most of the storms have weakened by now. This is the scenario from this morning. Again, put it in, not going to show all the maps for today, but we'll show enough to see how it worked. Shortwave trough, essentially over the high plains toward eastern Colorado. That's going to progress east. It amplifies a little bit with time. And again, we managed to get a special sounding from Springfield just ahead of storm initiation. So in this case, we've got a cap to warm sector, modest instability. Deep layer wind profile looks like it would favor supercells, all else being equal. Okay, so we've put in the boundary motion, and we've got the shear vectors, and let's look at how this one plays out. 0 to 6 shear looks pretty classic for supercells, pretty large boundary to shear vector angles, same thing with the storm relative wind. So first two elements would look like, hey, I think we got a shot. Storm motion relative to the boundary, it's going to be hard for the convection to move away from the zone of ascent in this case because the boundary's oriented north-northeast, south-southwest, and it's moving just fast enough to the east-southeast to make it difficult for storms to move away from the boundary. That would be a big hint toward a more linear mode. So again, mixed signals, and this is typical. So we look at we'll go to the visible image and look at how this played out. So again, some of you have already seen it, but we have the storms initiating southeast Kansas, northeast Oklahoma into Missouri. In this case, the storms were so close together that it was fairly strongly forced in that narrow band. And the storms almost immediately were overlapping, so we initiated storms very close together. Even though the shear vectors would say it might try to go discrete, the only way you would manage to do that is if you can get the storms away from the zone of ascent. So looking at the radar just roughly every 30 minutes, you see it sort of starts as this blob. The storms are very closely spaced to begin with, but it's trying to maintain some hint of discrete structures, but they're so close together and they just can't seem to get away from one another. But again, there were indeed some supercell structures in here. I didn't have time to grab the buoyancy fields and that sort of thing, but the idea here is it's also a very confined warm sector. This does not extend very far east, and eventually the outflow of the storms help move the convection even faster to the east, and it should be way on the east edge of the warm sector now. So it's just a case where the broader synoptic pattern did not favor long track discrete supercells, even if they managed to form on this boundary in the first place. Okay, so we'll just kind of summarize this and then we'll get ready to take a short break. The strength of the forcing for ascent seems to be one of the big keys as far as what you're going to get. And just if you think about, and I'll leave this exercise to you guys, think about the various sources for ascent, comparing a dry line to a cold front. And again, think of the ways that dry lines tend to move. A dry line is essentially a Lee trough. It's the way things evolve through differential advection. It's almost always going to be, it's perpendicular to the terrain that you initiate it from, which means in the central U.S. it's almost always north-south in its orientation. Well, by default, the flow that's responsible for that, the downslope, is out of the west. So you've almost always guaranteed, geometrically speaking, you've got cross-boundary flow in a dryline case. Not always, every single detail, but in general, that's why it's the case, because the mountains are oriented north-south, it's the westerly component across the mountains that matters. The shear vector stuff seems to matter more when you have weaker forcing for ascent, and the question is, can you get storms to not interfere with one another? So even if you do initiate just a few storms, you want to make sure you keep them from interfering with one another, and that's where the favorable shear vector and deep layer flow orientation probably comes in the most to short circuit upscale growth. So again, that's what we've got for the first part. We'll start up, according to that clock, 8:30. I don't know what real time that would be, but about maybe 8 minutes from now, we'll resume. And what we'll do is we'll change gears, and instead of looking specifically at convective mode, we're going to start getting down into some of the nitty-gritty details of what happens when storms are interacting, and some of it is related to the convective mode conceptual models that we presented. So we'll take about an 8-minute break, and then we'll resume. All right, I lied. I gave you 10 minutes, so good questions. So we'll go ahead and get the ball rolling and kind of take a little bit of a change in the strategy here where we look at more at storm interactions.
There we go.
Okay, we're good?
Yeah.
Hey, for this bunch, that doesn't even count as a technical snafu. I mean, at least the ceiling didn't fall on me. So anyway, we'll go ahead and look at some storm scale interactions. This is where we start getting down to the nitty-gritty details of what happens when you're dealing with individual supercells and storm interactions, and what does that say about subsequent tornado potential, since tornadoes are the focus of the workshop here. So we've looked at convective mode, and some of the ideas that we just talked about will be relevant here. Okay, we'll start back with another old favorite here, the El Reno supercell, because there were some interesting changes in the environment. And again, it shows the whole point of trying to take a linear extrapolation approach when you're dealing with storms like this is a dangerous way to lead yourself astray. Okay, so we've got what looks like a largely discrete, large supercell storm that's intensifying rapidly. What I want to do is I want to focus on the rear flank of the storm. So this is about the time, tornado's already going. The El Reno tornado's been around maybe 8 or 9 minutes at this point. But we've got convection forming to the west. There's already overlap in the rain areas, so we're raining into the rear flank of the El Reno supercell. The question that should immediately pop into your mind is, what is this going to do to the structure of the storm from here forward? We continue forward. Convection continues to increase to the west. We've just got more and heavier precipitation falling into the rear of the storm. This is near peak intensity for the tornado, but you can tell, look at just the change in the structure of the storm itself. Just, we're only talking 10 minutes or something over the maybe 20-minute time period. So from here forward, you have to think ahead. Do we expect a large, violent tornado to just continue through the Oklahoma City metro area, or is something going to change about the convective mode? Okay, here's where the tornado, this is just past peak. It's wrapped up moving across I-40. A lot of the unfortunate things where chasers were caught and I was almost one of them too, had already occurred just prior to this in the few minutes. And at this point, the tornado's rain wrapped and it's sitting on the interstate. But we've got what continues, and again, we're at 37 after. This is near the end of the life cycle of the El Reno tornado. We have what is becoming a supercell by itself to the west. Tons of precipitation falling into the rear of the original El Reno storm.
Let's time out for just a second here.
I guess we're going to time out.
Streaming issues. Yeah, I don't know if it's YouTube or what it is. Oh, wait, no, I just have it. Yeah, no, check now. Okay. Literally,
Does anyone know if it was actually working before that?
No, I was watching.
Oh, okay.
Yeah.
All right, well, I'll step back. Couple. So we've got the storms forming and raining into the rear of the original El Reno supercell. Again, look at how much precipitation's forming. So my question here is that what would you expect to happen with any subsequent mesocyclones and low-level circulations? Look at how much precipitation's forming to the west of this and raining into the backside. This is a completely different scenario than just 45 minutes before when the first tornado formed. Again, now look at the appendage. Instead of a nice classic hook echo, it's a very large area of precipitation. This would be opaque. You wouldn't see through this. The rear flank of the storm looks like its own core. And again, this is where it wraps up. What would you suspect is happening at this point? If we're dumping a ton of precipitation into the rear flank of the storm, that's going to change the character of the rear flank downdraft, everything else. This is going to favor much stronger cold outflow production. It's going to change the strength and orientation of the gust fronts, and in this case, it would appear likely that it's going to disrupt the potential for additional high-end tornadoes from here forward. And if you look forward, yes, we had another weak tornado into Oklahoma City, but if you look back to the west-southwest, you can actually see the fine line south of El Reno down US 81, you can actually see the gust front is now getting ahead of the convection, especially to the west. So this is a case where on the storm scale, we're changing the mode of the storm from a discrete supercell much more to a heavy precipitation type storm with a much different outflow character. It's possible that this whole evolution, if we go back to the very beginning of it, the fact that we had convection interfering with the rear flank of the storm almost immediately may have played a substantial role in the erratic behavior of the rear flank gust front and the erratic motion of the tornado initially, why it was moving so fast to the southeast, much to the right of the storm motion, why it accelerated, and then eventually the behavior was a little bit unusual. It's not unprecedented, but it was unusual. When you combine that with being a very large, dangerous tornado, this sort of thing, you can anticipate the odds of getting that sort of crazy interaction are much higher when you have storm interactions than if you have a discrete cell. So again, if you're responsible for deciding what's going to happen in Oklahoma City, if you just linearly extrapolate 2-mile wide tornado back to the west and it's just going to go straight into the metro area, in this case, how does that forecast turn out? You know, you can send everyone into a panic showing them the El Reno tornado. But the point here is that it was getting much more complicated quickly, almost immediately after the first tornado developed. And in this case, this looks much more like a flash flood scenario than it does a serious tornado threat from this point forward. Okay, so we'll look at, you have to consider how would I expect that to happen. Here's a case where the convergence is focused. This was a well-defined triple point case where stalled front and the dry line intersection back to the west of Oklahoma City. Convergence is strong. We actually had large cape. It's not capped very strongly in that area. So we have essentially a quasi-stationary initiation point. The El Reno storm moved off of that triple point, but new storms continually formed to the west. So it's a case where you may have had too much of a good thing going, and we just kept initiating storms, and then the orientation of everything changed. We go from discrete to more of a linear cluster. It goes more from dangerous tornado to a multi-hazard threat. Okay, so then there's other ones. This is just a messy picture this is June of 2009. It doesn't really come out in the picture, but there's a huge outflow surge with this. And what happens when various new cells form and interact with existing supercells, what can happen? Okay, here's our initial storm. That's just northeast of Dodge City. And looks like largely a discrete supercell. This has mid-level rotation. It's not very strong down low. You notice immediately, these will be every 10 minutes on the radar images. We see the little cell just to the south of the appendage. So we've got initiation, and if you look at the direction, it's moving, the initial cells are moving a little bit more with the background mean flow, and they're interacting with the rear flank or the hook echo region of the supercell almost immediately. Just like the El Reno case, if you start dumping a lot of precipitation into the rear flank of the storm, what was initially a rather narrow appendage, what do you expect to happen to cold outflow production? You might expect a big ramp up in the depth and strength of the downdrafts, and in this case, maybe some sort of surge in the rear flank gust front, and that's indeed what happened here. So you can see the fine line now, and we're looking in the area where the supercell remains discrete. It absorbs the new echoes, but it produces a lot more outflow than it was producing before that. And this continues surging to the southeast, but you look off to the east, now we've got another cell forming. This one's in a different location relative to the supercell than the previous one. Instead of hitting the rear flank of the storm, this is moving into the forward flank. If you consider what might be happening there, the forward flank is the preferred inflow region to the supercell itself. Now, we've talked about vortex stretching in the vertical. You can get the same thing in the horizontal. If anyone's experienced the accelerated inflow into a supercell, if you think about horizontal vorticity, if you're stretching that, the flow 15 knot inflow to 20 to 30 to 40 knots, you're stretching the vortex along a horizontal axis. So that would be reflected in larger SRH in the accelerated inflow region of the storm. This is exactly where this little new cell is forming and moving into. Well, it doesn't know about the background environment over the plains as a whole. It experiences this somewhat enhanced inflow region. Larger SRH, it's as moist or moister an environment than it was to the west. you might expect a more rapid evolution into cyclonic rotation with this new cell, and that's what happens. It goes up, the gust front from the original surge catches that, and somewhere in here we have actually a tornado forms. The previous one, circulation, was largely non-tornadic, but like the El Reno case, look at the whole mess of convection back to the west that starts raining into it. Even though you get what looks like a substantial tornado, with this sort of configuration, you could largely suspect that it might be one and done, especially in a plains environment where outflow production is a little easier to come by. And you can see the fine line moving southeastward, getting a little bit ahead of the reflectivity cores at this point. So we'll look at the velocity image. Here's a case, so I'll highlight the same areas. You can see the outbounds. This is in a storm relative sense. We get this surge, and if you look at the base velocity, that was about 60 knot winds. So this is enough to kick up blowing dust and low wind severe winds south of Kinsley, Kansas with that surge. But you can already see the enhanced inflow area, the storm relative inbounds using the motion for the larger supercell. That's the modified area that this new cell is going up in. It evolves pretty quickly, and it looks like you just sort of have a continuation of the original rear flank gust front, the new rotating updraft, and quickly we form a tornado, and there's a fairly strong velocity couplet in there. It didn't hit much, but it probably was a significant tornado, and it doesn't last too long because, again, the whole storm mode changed. So again, in this case, it gets pretty complicated. If you're out there in the field or if you're working warning operations or whatever and you want to anticipate what's going to happen next, you have to look at a lot of stuff. I mean, to get this right, if you just go outside the window and you look at the structure of individual clouds, it's pretty complicated. Well, if you really want to know what's going to happen, you have to be able to explain all these details. And I'm not claiming that I get this right every time I go out and look at it. It's just a lot of times I forget to think about some of these things, or you just make assumptions, and that's where you usually get yourself in trouble when you look back on it. All right. There can be other type outflow interactions. This is just a sorry picture of the beginning stage of a very weak tornado near Piedmont on a day that was otherwise non-tornadic, and we'll take a look at how that one evolved. This is one where you have right and left moving supercells, the outflow with one interacting with the other, and it changes things for the better in terms of tornado genesis in the short term, and then for the worse in the long term. So we step forward, it's clear that something's going to have to give. You can't have the storms almost moving at one another and not expect something to occur later. So you can see the fine line denoting the gust front with the left moving storm, which is producing severe hail. The southern supercell up to the north has a history of large hail and really nothing else. So it's been a slightly high base storm. LCL heights are modestly high. It's a clear supercell environment with deep layer shear and buoyancy, but the low-level shear and the LCL heights were on the marginal side. So this was not a particularly efficient tornado-producing storm. However, what happens with the environment as the gust front from the left-moving cell encounters the updraft region with the right-moving storm? So in this case, we have the interaction has already started, and think about what I said were the limitations of the environment. The low-level shear was relatively weak in the background environment, and the moisture was on the margins. What would you expect to change on the outer fringes of the gust front of the left mover? Would the low-level shear be stronger? Perhaps. Would it be a more moist environment? Probably so. And on the Oklahoma mesonet, we did have a couple of observations where you could pick that out, the dew point. And I was sitting there with Roger Edwards. We just happened to, one of the rare times we're in the right place, sitting there waiting, and we kind of wondered. I said, I wonder what's going to happen when this collides. And we went through some sort of elaborate argument and said, it just might give us a weak tornado threat short term. And sure enough, a tornado forms about a half mile to the northwest of us while we're sitting there. And it's right in that mess. That's what the storm looked like right at tornado genesis time. After the interaction, and notice it's about 10 or 15 minutes after the initial interaction, but look at what's happening to the cluster as a whole. This thing continues through, and it just turns into a mess. So what it does in the short term, it enhances the tornado risk, and then the collision of the outflow with the entire gust front structure of the original storm, it blows up. Now, that was a tremendous hailstorm in northwest Oklahoma City area, but it actually essentially undercut the original supercell. The whole thing grew upscale into a cluster. You can almost not even see that. I didn't want to zoom in so much, but that tiny little velocity couplet is the weak tornado. But there were no tornadoes with any other storms at any other time on this day, so this is a case where, again, if you're interested in finding these or sniffing these out, the key was the storm interaction in the short term. But it also severely reduced the severe threat with that original right-moving supercell only 20 minutes later. All right, now here's one. I think this is the Chickasha, Newcastle tornado from May 24, 2011, while I was in here with Noah's Ark going on and the animals and people running around everywhere. So I didn't get to see this, but I guess I have to believe people when about 100 pictures of it come back, but it must have occurred. But we're going to look at that case because that was a fascinating storm interaction and environment change case where I don't know how many people have gone back to look at what happened in the short term. So here's where we start. We're 5:15 roughly in the afternoon. We've got the Chickasha tornado has already formed right about now, and the storm to its south, there in the left middle, that would be the Goldsby supercell, is just cranking up at this point. But look just south of that one, the opposite inflection, that is a remnant right mover that came up way down from North Texas. Now, when we talk about the convective mode stuff, this was a case that had the shear vector orientation almost perpendicular to the boundary. In that scenario, occasionally you get left splits and right movers. The motions are so different that they can't interact. Like the left movers move much more to the north, and the right movers are east, and they cross paths on occasion. So you see this usually out in the central U.S. This is typically Kansas, Oklahoma, Texas type occurrence. But it's one where if the shear vector orientation is too large and the environment isn't completely and immediately favorable for cyclonic storms, you'll have these left movers hanging around. May 10th had some of that going on as well. So we have a left mover moving up from the south, and then we'll jump to the interesting time. So 22/3, 5:30, we've got two likely debris signatures in the lowest reflectivity cut, and this is confirmed with everything else. Very strong velocity couplets, two violent tornadoes ongoing. Norman's just 15 miles or 18 miles northeast of there. So if you're sitting here at the Weather Center, you would probably be paying attention at this point. You've got tornadoes moving toward either northwest and southeast Norman at the same time. But we've got this little left mover to the south. What's it going to do? It continues up. It looks like it's already starting to interact. Now, the other thing I'd want to point out is what is the Goldsby storm doing to the Newcastle storm in terms of where its precipitation's falling relative to the inflow region of the Newcastle storm, which is the northern supercell? Everything's fine right there. It now starts to rain. Moderate to heavy rain is falling in the inflow region. So you might think that the southern supercell at some point is going to start to interfere with the intensity of the northern storm just by reducing buoyancy. At the same exact time, we have a remnant left mover that's weakening. Its outflows collided with the mesocyclone of the southern cell. So we continue north. Southern cell looks fine at this point. There's rotational velocity, 80 to 90 knots. This is still producing violent damage at this point. And the left mover looks like it just disintegrated. Okay, you might think, well, okay, there's no influence at all. Uh-oh. Now the storm weakens. So, this is literally right on Norman's doorstep. The tornado was about 2 miles south-southwest when it dissipated. So the question here is, the popular opinion might be that the left mover killed it. And so it's certainly a possibility, but you do notice that the left-moving storm was much better defined earlier, and it actually is just kind of fizzles away after whatever interaction occurs. And then we have a storm, but notice down to the south, that other storm was going, and it starts to lose some of its structure. Now, it's not clear that we can blame that on the left mover that has now dissipated and is 2 counties to the north. So this is a case where you have to consider the environment. So let's look at how the environment has evolved over time in this case. So we've got strong buoyancy, only a small area that's relatively uncapped out right east of the dry line. That's at 21Z. 22Z, notice the inhibition has already started to come up everywhere. So the buoyancy's gone down slightly. Inhibitions come up. 23Z, inhibition continues to increase. So essentially, we're looking at the fact that the warm sector is already starting to stabilize out east of the dry line. Now, if you remember from that day, it was actually pretty cloudy along and east of 35. So it didn't warm up much east of 35. And look down in North Texas, that's a Cape hole. That's lower buoyancy and much larger inhibition that is feeding in. So it's probably a reflection of it's just a cooler boundary layer. So the dew points didn't drop off, but it's cooler temperatures. So this is a case where we had a left mover that survived that you could potentially anticipate with the general shear vector orientation, say, well, there's a chance that kind of thing could happen today. On a north-south dry line, I might worry about east or north moving or north-northeast moving left movers interfering with right movers. This is hardly an isolated case. But at the same time, the environment has already started to deteriorate in terms of its being favorable for tornadic supercells about the same time the interaction occurs. So in this case, we may have had two strikes against it. We had peaked the environment, and we had a negative destructive storm interference. So again, very complicated. I want just to impress on everyone, just go back and look at this mess. You're a warning forecaster. You've got two confirmed, probably violent tornadoes. You don't have damage survey stuff yet, but these are serious tornadoes ongoing. They're heading toward heavy population, and they're about 15 to 20 minutes out. And it turns out neither one of them made it into the population, and there really was no disaster in Oklahoma City. Again, think back to the El Reno case. It's very difficult. Unless you have purely discrete storms where there's no interaction, no interference, a lot of the evolution in time forward from when you're taking your snapshot can be pretty complicated. And you don't have a chance of getting it right if you don't think about it. And I'm not saying that it's always easy to unravel all of these processes at once. But if you're not thinking about it, you'll just blindly say, oh, well, large violent tornado, steady state, for the next 3,000 miles, it's going to move northeast and hit everything. And when it moves off of Nova Scotia, then we quit worrying about it. Well, chances are it's probably not going to evolve that way. Something's going to change. And in this case, there's a lot of complicating factors way down on the storm scale. All right. Now, there are other ones. I don't know if anybody has any earthly idea what this one's from. This is a cell overtaking a line. I think you can tell from the date of the publication and that this is pre-88D network. So this is the Huntsville tornado from November of '89, produced EF4 damage. And this was that SC1, that's a supercell that was in the warm sector, non-tornadic until the Squall line overtook it. Produced a violent tornado right as it moved into Huntsville. And then that was it. That was largely the only tornado of the day. So that might be a hint, maybe, on this one. This is May 24th, 2011, same day as what we just looked at, but this is closer to 5Z, so we're getting close to midnight. 11:39 p.m. Central Daylight Time. We've got what looks like a supercell sitting in western Arkansas. That's the Fort Smith radar site. So we're looking in western Arkansas right now. You have this cluster of storms. It's not really a line. It's sort of maybe slight bowing tendencies, but it's this cluster of storms moving in from the west. The question is, we've seen in some other cases the interactions are negative. Well, it's not always destructive, and you have to consider, can this change what's going on in the low levels with the storm? And I'll admit up front, this is going to be very difficult to anticipate when it's going to be destructive or constructive, depending on tornado, whether it favors or harms tornadogenesis prospects. Okay, at this point, it looks like our supercell is getting a little bit more organized, but boy, it's got an awful heavy core is about to impinge on the rear flank. So just, step through a couple of times. What I've highlighted there is right as that interaction occurs, what do you think that little red splotch is, the higher reflectivity? That signifies lofted debris. There's the start of a violent tornado with this storm. There haven't been very many tornadoes over the past 2 or 3 hours in this event, and I would worked right up until 5Z on this event. So it keeps going. You would think, well, it should change everything, but notice one thing that is curious about it. The little debris signature, and I'll show the velocity in a minute, it manages to keep pace with the cluster. So it's not really being clearly overrun. It kind of catches up with it. Now it's moving with the original cluster. So it's still going. That's all still tornado. And you notice the original cluster where it merged sort of weakens right there in the vicinity of the rear flank of the supercell. And that new echo to the east-southeast, that's actually a new storm. So these are 10 minutes apart. So that's not a continuation that just to the southeast of the circle, that's actually a new core that's forming to the east. So this is a case where the cluster itself, notice how much smaller it is. It actually seemed to weaken over time, interacted with the supercell, and then we ended up getting a big tornado. And looking at the velocities, weak cyclonic shear, convergence down low, until the other thing shows up. This is right around the time the gust front catches up with the rear flank of the supercell. Now we start to see a tight circulation. That's the signature of the tornado. At this point, it's producing EF3 damage, I believe, and went on to produce EF4. So it just continues. We've got a strong circulation, and we even get a new couplet forms with the new cell that's out to the southeast. So this is one where if you just blindly say, oh, well, there's going to be storm interactions, it's always going to be negative. Just remember, it depends entirely on the details. And there is some precedent for this sort of interaction leading to subsequent tornadogenesis, especially in cases where storms were not tornadic before that. It seems that perhaps it's related to what it's doing to the low-level updraft as the gust front collides with the rear flank of the storm. Some of it's just speculative. I mean, some of that area is pretty wide open for some interesting work to be done. So storm scale interactions, again, just to keep in mind, it can be really complicated. I only showed a couple of examples. There are thousands of variations on this theme. If you have a marginal environment, what we're doing here is the key is if the large scale or mesoscale is not providing the environment favorable for tornado formation, is there something on the storm scale through the interactions that can provide that environment? It's going to take careful attention to details to figure that out, whether you're in the field, whether you're sitting behind a desk, whether you're here at the student lab, whatever you're trying to do, if you want to figure this out, you can't just gloss over things. You have to keep the meteorology in the forefront of your thinking and not let I'm excited because this looks interesting, or, well, it's not evolving the way I wanted it to, therefore I'm going to get bummed out and just blow it off. You got to keep thinking, and that's the tricky part, is sort of turn off the emotional response and try to think meteorologically as best you can. Of course, you can reduce the tornado risk, and that seems to be the most common influence. And in this case, it's anything that boosts cold outflow production too much by the parent storm you're interested in, or the outflow from the storm essentially interferes with the inflow to the existing storm and reduces its inflow of moist, warm air that's sustaining the deeper updraft. So again, hopefully I've given you some stuff to think about. If you start watching the radar, watch the environment, you're going to see that there's all sorts of crazy stuff happening all the time, especially a lot of times when you're not watching. If you're only focusing on, the central plains from 21Z to 1Z, and then it's dark and then you don't care, if you get a chance, look at some of the other stuff. There's a lot of weird stuff that happens overnight, and some of that plays into part of the reason why it's much more difficult to do a convective outlook on the national scale than it is to just make a chase forecast, because you have to anticipate these sort of things as best you can, or where the possibility exists. All right, well, next week, or actually 2 weeks from now, this will be the last week off, will be next week because I'm working night shifts. We will go look at some of the climatology of the supercell and tornado ingredients, how they vary by region. We have some work that's fairly recent that looks at that, and we'll talk about how things vary, and then to where you can put it in perspective. What is large CAPE for the plains? What's large shear for the southeast? That sort of thing, and then we'll look down on the tornado scale and some 88D signatures and some new stuff that we've been working on that could be of use in trying to anticipate what a storm's doing in real time when you may not have tornado reports. So again, that's all I have for this evening. I appreciate the brave souls who showed up and did not go to Missouri. So I applaud you, even if you were stuck here because you have a quiz or whatever the case might be. I appreciate you being here, and we'll pick up here in 2 weeks. So thanks, everyone.